Greetings, class. This is a YouTube lecture, what will likely be part one of at least 2 or maybe 3 segments. I'm going to try to keep each segment to 10 minutes or less for ease in uploading. But this is just FYI, this is for my statistics class, not my community corrections class. However, I only have one YouTube channel, and I'm going to just put this video on that channel. So if you are in my community corrections class, this video is not for you, despite the fact that I'm wearing the same hoodie that I was before. Anyway, in the segment that I just posted for you. Today we're going to talk about a special type of probability distribution. That's really what today's lecture is going to be about. I would caution you, however, I highly recommend that if you have not done so yet, that you make sure that you download and print the PowerPoint presentation titled Samples and Sampling Distributions first. Also, under the subfolder called Documents, I've placed a document simply called Supplement to the YouTube Lecture on Sampling Distributions. That's under Documents. So if you haven't done so yet, go to Blackboard, or pause this video first, go to Blackboard, and then get the PowerPoint presentation on samples and sampling distributions, and also get the supplementary document that I posted under the subfolder Documents. As I mentioned just a little bit ago, today's subject matter is going to be all about samples and what are referred to sampling distributions. Now, sampling distributions are just a very specialized type of probability distributions. You've already been working with a couple of different probability distributions. We began, as I mentioned before in class, we began discussing the issue of probability using the rectangular probability distribution just as it is introduced in SPATS. And the rectangular probability distribution was used to demonstrate just the basic constructs about probability. The fact that we can add and subtract probabilities which correspond with area in the picture, area under the curve. So if you'll recall, that's part of the language or part of the lexicon that I'm hoping that you're internalizing now, the area under the curve. Because when we talk about probability, that's really what we're referring to, is finding out specific area under the curve, regardless of the shape of that curve. Now, as I mentioned a couple seconds ago or a couple minutes ago, sampling distributions are simply a special type of probability distribution. Now, if you recall, a probability distribution is, among all other things, it is theoretical in nature. And think about what makes a probability distribution theoretical in nature. It's based on an infinite number of trials. Now, I know that might be kind of difficult to conceptualize, but that's essentially what probabilities are based on, an infinite number of trials. Probability distributions are based on what we would observe if we had unlimited resources, if we had unlimited experiments, if we had unlimited trials. And sampling distributions are largely the same thing with a little bit of a twist. First of all, within the context of this class, you have studied several statistics. And think about what some of those statistics are. You've studied the mean, you've studied the median, you've studied the mode, you've studied the standard deviation, you've studied variance, you've studied many different types of statistics. All right? Now, you have studied those statistics within the context of just one sample. All right, think about that for a second. In other words, whether it was in class, or whether it was on a problem set, or whether it was on an exam or a quiz, you were given one sample. You were given a set of cases, all right? And you were asked to take those cases, to take those data points, and calculate, for example, a mean, or calculate a standard deviation, or calculate a variance, for example. Each one of those statistics has its own theoretical sampling distribution. And each statistic's sampling distribution has a unique shape. All right, so, and again, I realize this is theoretical in nature. We're talking about the theoretical underpinnings of inferential statistics. So each statistic has its own theoretical sampling distribution. So the mean, for example, has its own sampling distribution. The variance has its own sampling distribution. The standard deviation has its own, again, theoretical sampling distribution. And each of those sampling distributions has a unique shape. So the sampling distribution for the mean has a different shape than the sampling distribution for the standard deviation, which has a differently shaped standard deviation than the variance. Now, today, or for the purpose of this video, we're going to discuss the sampling distribution for the mean. And this is a slide from your PowerPoint. Today's statistic, or the mean, has what's referred to as a normally, and please note the single quotes, not double quotes. I don't mean that literally, I mean that approximately, has a normally shaped sampling distribution. Now, what does this mean to say that the sampling distribution for the mean is normally distributed? Or, to be more precise, the sampling distribution for the mean is approximately normal. And here's what we mean by that. When we say that something is distributed normally, essentially, this is what we mean. Let me shed some light on that. As you can tell, I'm filming this in a high-tech studio. This is what we mean, and again, if you can't see this very well, that's okay. That's why I asked you to print it out so you have it. This is essentially what we mean when we say that something is distributed normally. We mean that the distribution is bell-shaped, it's symmetrical, and that when we move 3 units to either side of the mean, we have encompassed nearly all of it. Look at that handout, and in fact, pause this video if you want and look at this handout that I was just holding up of the bell-shaped curve. When we say that something is normal or approximately normal, we're saying that it is bell-shaped, that the mean, the median, the mode are at the top or the peak of that distribution, and that once we go, and you've seen me do this before, right? 1, 2, 3 units beyond the middle, we've accounted for nearly all of it, right? So that's simply, this is nothing new. That's simply what we mean when we say that something is distributed normally. Now, the sampling distribution for the mean approximates a normal distribution, right? So in other words, it approximates all those properties. All right, now, imagine. I want you to imagine. All right, use your imagination. Imagine that we were to draw, and I'm referring specifically to another slide, the next slide in our PowerPoint presentation. Imagine if we were to draw 100 samples, all of the same size, from the same population with replacement. All right, imagine that. So imagine, if you will, like a bag. Imagine a bag full of 100 chips, right? Poker chips. And one sample meant reaching into that bag 8 times and pulling out 8 chips and seeing what numbers were on those chips, writing those numbers down. That's one sample. Okay? Then you throw those chips back in the bag and you shake it up. And you reach in and you draw 8 more chips from the bag. All right? That's your second sample. And you write down the numbers that are on those chips. All right? That's your second sample. And you throw those 8 chips back in the bag and you shake it up and you draw a third sample of 8 chips. And you look at the numbers that are on those chips and you write those numbers down in a group, and that's your third sample. Then you throw them back in the bag and you shake it up and you draw a fourth sample of 8 chips. And you write down the numbers that are on those chips. That's your fourth sample, right? Then you throw them back in and you do that over and over and over again until you've reached 100 samples. All right, that's segment one. We're almost at 10 minutes. I know you can hardly wait to see what comes next.